All right, so in example 5, we're going to talk about impossible events, which is just finding the probability of rolling an 8 when rolling a standard fair die. So how many possibilities do you have when rolling an 8? 0. So you'd be surprised. Because it is impossible to have an outcome of 8 when rolling a 6-sided die. Any questions on that? Pretty straightforward. Awesome. All right, so if an event A this needs to go away. If an event A must happen or is certain, close enough, the probability of A is 1, and P of A would equal 1. So basically, if, again, I ask the question, oh, it's going to be very delayed. If I ask the question, what's the probability of getting 1 through 6? How many options do I have? 6, right? They all have there's 6 numbers on a die. I have 6 possibilities. And then how many possibilities are there? 6 as well. And then 6 divided by 6 gives me 1. So that's that 100% there, that probability of 1. All right. Then we're going to look at example 6, which is find a certain probability. So this one says find the probability for a certain event. Find the probability of rolling a value less than 7. So kind of the same concept. So how many numbers are less than 7 on a 6-sided die? 6 numbers. Very good. And then how many possibilities on a die do I have? 6. So then 6 divided by 6 is 1. Very good. So you have 100% of getting a probability that's less than 7. Questions on impossible or certain events? All right. So let's talk about complementary events. All right. These are events where there's multiple things happening, but one kind of depends on the other. All right. So complementary events. The complement. Oh, wait, I think I got ahead of myself on that one. So complement is of an event A is the set of outcomes in the sample space. The complement of an event A is the set of outcomes in the sample space that are not included in the outcomes of event A, and we denote it as A bar. Right? So if you kind of go by the example we just did, the probability that you get a number less than 7 was what? 1, right? It was 100%. And then for the complement of that, it would be what's the probability of getting a number greater than 7? Well, that would be 0, right? The complement and the event A both have to total up to 100%. So basically, if you know event A is, I don't know, 3/4 or something like that, then the complement will have a probability of 1/4. Right? That's basically all that means. Basically, complement means what's the event of your thing not happening. Right? So in example 7, we're going to find the complement of an event. So event A is select the day of the week that begins with a T. What days start with T's? Tuesday and Thursday. All right. So what's the probability there of selecting a day of the week with a T? 2 out of 7. Very good. Event B, you're going to roll 2 die and get a sum that is an odd number. That is, well, 1 should be in there too. Oh, well, you can't get a 1 with 2 die. So that'd be 3, 5, 7, 9, and 11. So how many possibilities do we have in total for die of just sums? That would be possibility of like combinations, but how many different sums can we get? Close. It'd be 11 because we can't have 1. So you'd start with 2. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 because we can't add up to 1. So therefore, this is a 1, 2, 3, 4, 5 out of 11. Right? So for that event. Now we're going to put all this together. On die, on the sum, no, 6 plus 6 is 12. Yeah, but we don't have one. So if you get snake eyes, the lowest sum you can get is 2. So huh? Yeah. Right. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No. How many possibilities of sums do we have? Yeah, 2, 3. It's a sum probability. So there's only 11 different options of sums for 2 die. So the top part is your event happening. What's the probability that they'll be odd? Well, I had 3, which is 1, 5, 7, 9, 11. So my top number is what I want. So that's 5. On the bottom number is all the possibilities I have. Well, I only have 11 different sums that I can get. Right. Yeah, we just start at 2 because we can't add up to 1. All right. Everyone got that? Any other good questions like that? All right, let's answer the questions that follow. So again, it says on part A, it says the complement of A, which is the single days of the week with T, which is Tuesdays and Thursdays. If you're asking for the complement, right? So technically, they go into a lot of work here. So, and I'll do it, but I'll show you the real quick math here. So we just calculated what's the probability of getting a T on a in the week. 2 out of 7, right? The way they want you to do it is, what are the other options that don't have a T in it? Monday. Perfect. All right. So that's kind of what they're doing here. They're saying, all right, well, this will then be Monday, Wednesday, Friday, Saturday. Yes, that's what they're wanting here. And Sunday. But the answer is, what's the probability that that not happen? Well, we can see how many events are going to not happen that land on T. 5. Very good. And how many possibilities were there? 7. All right. That's them doing it. But the math is so much easier. If you know what your A is, which was 2 sevenths, just do 1 minus 2 sevenths. What's 1 minus 2 sevenths? 5 sevenths. Gotta love a day when the internet doesn't work anymore. All right, so there you go. So they wanted the options that you had so you could calculate the 5 sevenths. But in reality, the way I've always done it is I just figure out what the original event was and subtract it from 1 to figure out what the event of it not happening, which is this 5 sevenths. Yeah. All right, so if you're told to list it, that's how you do it. But if you're just asked for the complements probability, just subtract it from 1. It just makes more sense in my head. Any questions on that part though? Let's look at part B then. So in part B, again, we're trying to find the complement of rolling 2 dice that give us sum that is odd. Well, you calculated that was 5/12, but then it wants you to list all those options that are not odd. So that would just be 2, 4, 6, 8, good. 10, 12. And that right there is how many options are there? 6. And then what was the total amount? 11. But once again, if you know what the original B is, what is 1 minus 5/11? 6/11. Fractions? Gotcha. Okay, to do fractions, they have to have the same denominator. So 1 is the same thing as 11 over 11. And as once the denominators are the same, I can just do 11 minus 5 and get 6. Right? Any other good questions like that? So if they ask you to list it, list it. But if they're just asking for the probability, let's do 1 minus whatever the original probability was. Which is then what it gets into on this next part here. So again, this last part here, it says if the I'll say the last part. If the probability of an event or the probability of its complement is known, then the probability of the other can be found by subtracting the known probability from what value? 1, right? Because the probability and the probability's complement must equal what? 1. Very good. Go ahead. It just depends. It just depends on what the question's asking. So sometimes it does want to know what are all the things that would be its complement, or if it's just asking for the probability. So if I was to write it like this, hey, what's the probability of the event A not happening, the complement of A? Then all I got to do is just do 1 minus the probability of the A actually happening, right? And then sometimes, in my opinion, sometimes it's just easier to find out what straight up what the complement is. Like if I know it's asking, hey, what's the complement of not getting a T? I'll be like, all right, well, how many days of the week doesn't have a T? And that's like, all right, well, the answer is 5/7 without actually having to do the subtraction. But it gets a little harder when we get into some deeper probabilities where you're like, oh, I don't know this one, and then just subtract it from 1, right? Or find the event. So now you're looking at Venn diagrams, looking at compounded, meaning is it an or case or an and case? Yeah, and then sometimes finding that in the subtraction one is easier than just looking for what it's not or in that situation. So yeah, it just depends on the situation. Both directions give you that one. And then saying concept again, maybe it's easier to find the complement, subtract from 1 to find the original event as well, which is what you were just talking about. So sometimes finding out who doesn't drink the alcohol, subtracting that from the total will give me what is with alcohol. That's it. And again, the event and the not event happening, which is the complement, needs to equal to 1. All right. So then we get into empirical probability. What do you think this blank is? So the empirical probability relies on actual experience or observations to determine the likelihood or relative frequency of outcomes. So given a frequency distribution, the empirical probability of an event being in a given class is this. So you have the frequency for the class of interest. So if I want to know what the probability of y'all liking math, I would have to do a survey. Let's say all 6 of y'all said y'all love math. 6 will go on top because my frequency, and then total frequency in the distribution. So I had 6 kids in my class. So then that becomes 6 over 6. So 100% of y'all would like math, right? It better be 100%. Now, it's got to be more than just like. We got to love this. Let's look at an example. So in example 8 here, it says a survey of blood type of 50 people revealed that 21 have type O blood, 22 have type A blood, 5 have type B blood, and 2 had type AB blood. Not looking at any positives or negatives here. And then it gives us the chart as well. So we have our total of 50. This is our frequency distribution chart. Now we're going to use that to find these probabilities. So this one says using the frequency table, we can find all of the empirical probabilities. Right? So we can find the empirical probabilities. And it does the work for you, and I really hate that about this. But we can look at it, and it says if I want a person that has type O blood, I literally just go here and go, well, there's 21 for that. So that's going to be my top number because that's what I want. So I put the well, this is all wrong then. So a person that has type O would be 21 people. Good. I'm glad they did get it wrong because we can do it better. Oh, perfect. We'll fix that. And then from there, we can then take the total amount in our sample, which in this case was 50. I'm going to be honest with you on a free response question. You can leave it like this unless the fraction can be simplified. If it's a multiple choice, they might have you write this out as a decimal. You can type in calculator, get it, or just realize that you can multiply these by 2 and get 42 over 100, which is just 0.42. I'm good either way. Just know on a multiple choice versus a free response. Any questions on how to do that? Or are you still straightforward? All right, we haven't gotten to the hard stuff then, I guess. All right, this next one says a person had type A or type AB. When you see the word or, you're going to add up their frequencies, right? Or probabilities, or whatever the situation might be. So I have 22 type A and I have 2 type AB. So what is 22 plus 2? So I get 24. But then how many are still in the sample? 50. So it's still going to be 50 over 24. Again, on our free response, I would expect you to be able to simplify this down to 12 over 25. If you wanted to convert that into a decimal, you can, which is just 0.48. It does not matter to me. Questions on that kind of math? Yes, ma'am. Go ahead. I just love fractions better. But as long as the decimal is an exact decimal, I'll take it. For instance, if the answer is 1/3 and you tell me it's 0.3, you're wrong. You would have to write 0.3 repeating to indicate that you are 1/3. So to save from that mistake, I would just go with fractions. But at the same time, multiple choice might have the decimal version and you need to be able to go backwards and forwards with it. So go decimals to fractions and fractions to decimals. Good. Any other questions? All righty. This next one here, it says a person has neither type A nor AB. So the best way to do this, and this goes back to finding the event of A and then subtracting from 1, is let's find the event of A and AB actually happening. So type A I see is 22. Type AB is 2. So I get 22 plus 2, which is 24. All right, that's the event of A actually happening. This is the complement of that. So I then need to do the 50 out of 24. And how much would that be? 26. So then I can see, all right, that's 26 out of how many total people? 50. And then I can reduce that to 13 over 25. And you can kind of see that's what they did here. They took the event of probability of A happening to get our probability of A not happening. Actually, vice versa. This is actually not A happening, which is the is happening. And this would be not. Right. Questions on that? So again, sometimes it's easier to go the other way. Yes. Exactly. You could do that too. I'd be like, all right, I want type A and AB, so I'm just going to ignore those two, and then I'm just going to add 5 plus 21 and get 26. Yeah. Multiple ways to get to the same conclusion. Any other good questions? All right. Let's get into some more notes here. So empirical probabilities have the same value as the relative frequency. And if you remember, our relative frequency were always decimals, And the decimals always added up to what value? 1, right? That was actually a test question, right? So relative frequencies must add up to 1. So relative frequency of the outcomes in this distribution. So law of large numbers, something to know. Hint, hint. The law of large numbers. Big shocker that was the spaces, huh? States that as the number of trials of a random experiment increases, the empirical probability will approach the classical or theoretical probability. Meaning, we did in chapter 1, we flipped a coin 5 times. It happened to land on heads every time. So we had a 100% heads, 0% tails. But what is the theoretical probability of each one? 50-50. So if I would have kept doing that maybe 50 times or 100 times or 500 times, those probabilities will get closer and closer to their theoretical probabilities. They'll eventually become 0.5 for each one. That is what law of large numbers states. If I do the trial over and over and over again, eventually I'll get closer and closer to the theoretical probability. Yes? No, it's just law of large numbers. So just think of a really large number, like 1,000 trials or something. What's a Google? What's that? Is that a number? Like a really long number? Yeah. If you want to do it that many times, yeah. You just basically, it's just saying the more times you do it, eventually you'll get to that same thing. And you could have 2 flips, right? And get heads and tails and have that 50-50. And it's a really small number. But then you do it again and it could fluctuate. But you do it, whatever number you just said, those probabilities will get closer to each other. Like 100 zeros? Yeah, you could do that if you would like. All right, on this next part here, it says, suppose a fair die is tossed. The classical probability of each value from 1 is, or 1 to 6 is 1/6 because they have the same equal opportunity of getting it. For an experiment using a fair die, as the number of tosses that result in a 2 increases, the theoretical, oh, my bad, the empirical probability of tossing a 2 will approach the theoretical probability of 1/6. So basically, again, what it's saying is I can roll the die twice, it land on 2 twice. But if I do this 1,000 times, that 100% of landing on 2 will then eventually go down to its 1/6 probability. Any questions on that, on large of all numbers? Very important to know. Big stars here, guys. Make sure you know that one. Oh, wow, this only had like one little thing on it. All right, so if a die is tossed many times, no, did I already do this? Oh, I did not. Okay, so if a die is tossed many times and the empirical probability for tossing a 2 is not approaching 1/6, then it is likely that the die is what? Weighted or not fair. Right? So if I was to take a die and I do it 1,000 times and I do not get that 1/6 for each number, then this is probably a loaded die or a not fair die. Bet you could get one like at Spencer's or something. All right, let's look at this last part of 4.1. So it says subjective probability. Subjective probability, that is your blink there. Again, big shocker. Is based on an educated guess or an estimate, an opinion, and inexact information. The probability is based on the person's experience and evaluation of a solution. For instance, a weather forecaster predicts 65% chance of rain, or a sports writer may say there is a 70% chance that a particular team will win the pennant that year, are examples of the use of subjective probability. So again, you're talking about an expert person saying there's going to be 65% chance of rain, where someone that's not an expert might go, there's a gray cloud, I bet we have rain. like a 100% chance, or I don't see any clouds, so no rain, but he's saying 65. So it's going to be subjective towards your experiences and your opinion. So that's a subjective probability. Go ahead. Yes, because it's going to draw from their own experience. Like for instance, let's take a Ford, right? Find on road dead is typically what happens to Fords, right? Oh, that's just me. But I don't have good experience with Fords. So I'm going to say that 75% of Fords are going to break down on you because I've owned four of them and three of them broke down on me, right? Or flipped over, and you can't park them upside down very well. So that's going from my personal experience, but you might actually have had success with Fords. You might have had 4 Fords and never had a problem. So you're like, well, Fords are 100% never going to break down on you. And you're getting it, you're subjecting it from your own experiences or opinion. Go ahead. What's the question, Charlie? No, this one didn't work anymore. And I just had 2 new shoes on it too. So it was a real bummer. That's actually every time I've either wrecked a vehicle or sold a vehicle, I just put new shoes on it. You said restroom? Yes, mm-hmm. Literally before I do it now, I'm like, we're not planning on selling anything today, are we? All right. So that's the conclusion of 4-1. Any questions on 4-1 that maybe y'all had in the homework? 4-1 was pretty straightforward. Do it. Let's make sure we get all the chapter 3, and now you should be able to do 4-1. And then let me teach you 4-2, so maybe you can do that as well. Yes. Then get to 4-3. Look at us sketching up. 10 pages, that what you just said? We can do it. We can do it. All right. Move fast. All right. The addition rules for probability. This is going to be your OR situations. So find the probability of compound events using addition rules. So mutually exclusive events. So these are events that cannot occur at the same time. That is events that have no outcomes in common. No outcomes in common and are mutually exclusive or disjoint events. Basically, what this can be is take that example we did in 4-1. What's the probability that you get a T in the middle of the week? Was 2 7s. And then what's the probability that you're going to get an even on a sum of die? 5 7. Did those 2 events have anything to do with each other? No. So they are mutually exclusive, basically meaning one did not affect the other. Okay. Does that make any sense? So mutually exclusive, one event does not affect the other event. So events that can occur at the same time are not mutually exclusive. Maybe I just got that backwards. Hold on. So events that can occur at the same time. I think I got that switched up. So the example I just gave you actually would be a mutually exclusive because I could technically pick a day of the week and roll a die at the same time. They have nothing to do with each other, but I could do those 2 events at the same time. A mutually exclusive one where I could not events that cannot occur at the same time would be like if I roll the die twice. The same die. Like I can't do both of them at the same time. I have to do one event and then do the next event. So yeah, so mutually exclusive is I can't do the events at the same time. Like if I did maybe picking a card and rolling a die, that would not be mutually exclusive because I can do both of them at the same time. Go ahead. Like the probability of like a part breaking, maybe. Well, no, because you have to have some type of probability of an event, not just 2 things. But they're two separate parts. At least it was two separate ships. Uh-huh. 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 So now it's a new ship. But you just used old parts. Yeah. So those would be, I would say, are not. Yeah. So again, cannot occur at the same time. So those would not be mutually exclusive because I could have the same broken part at the same time. So events that can occur at the same time are not mutually exclusive. You would basically be like, what's the probability of the same part, maybe, where like it can't break at the same time. It can only break once. And now we're getting technical. I don't think that's a very good probability one. Yeah, I'm just in general that piece breaking, not like two like different problems with it. Yes, it's like 0 and 1 codes. Yeah, right. It's just broken, regardless if like the belt broke versus a cylinder breaking or something. Like it still broke. Yeah. So now that we're really confused on what mutually exclusive is, let's do some examples. All right. So determine if the events are mutually exclusive and which events are not. So roll 2 dice. Event A, roll has a sum of 7. Event B, rolling double. Is this mutually exclusive? Yes or no? Can these two events happen at the same time? No. So therefore, they are mutually exclusive. Yeah, but it's the same 2 dice. Like before I can do the second event, I have to do the first event. They don't have nothing to do with each other, but I cannot successfully do this second event until my first event is done. So this would be mutually exclusive. Again, basically all mutually exclusive means is I cannot do both events at the same time. Right. So again, if you go back to that thing, events that have no outcomes in common are mutually exclusive or disjoint events. Basically, events that occur at the same time are not mutually exclusive. These events cannot happen at the same time. Huh. I like it. Think of it like a X and Y situation. I like it. You can't do two things at once. One has to happen before the other. So then we look at B, it says select a registered voter. So event A, the voter is registered independent. Event B, the voter is a registered Republican. I like your argument. I like your argument. Okay. Okay, so let's see in the point of their view. So in this case, it's the same roll 2 dice. They need to be more specific there. Like I say, the same 2 dice to make it mutually exclusive. And on this part B, what they should add in there is one person selected a registered voter at a time. And then now it becomes more because this answer here is mutually exclusive. But I love your argument because technically, if there's multiple people in this study, I could pull a person at the same time. But the events cannot happen at the same time. So if I'm one person randomly selecting people, then I can only randomly select one person at a time that might be independent. It might be, what was the other one, Republican or something like that. But I have to do one before I can do the other one. Maybe. I don't know. But this is why I'm not a huge fan of statistics. There's too much gray. But this will technically be a mutually exclusive, but I think they need to add in a single person is selecting people. Yeah. Because if there's multiple people selecting, I could technically do those at the same time. Well, let's look at part C. You said it's mutually exclusive as well? Right. And so the event can happen at the same time. right? So if I got a queen of hearts, jack of hearts, or king of hearts, is ace technically a face card? No, it doesn't have a face. All right, so this would be not mutually exclusive because I could pull those two events at the exact same time. Yes, but that to me doesn't work out very well. So this one's not mutually exclusive. So I can see this one being a very challenging homework, but most likely also probably a true false question. Both of those is you. I thought it was a test. I'll give you that point. Okay. Can you send me an email? Because I'll forget. Yeah, send me an email as a reminder. Nah, I believe you. Yeah, I don't know. I don't remember. All right. So let's go away from mutually exclusive. I say that we're going to talk about mutually exclusive events here. All right, so events that are mutually exclusive, when two events A and B are mutually exclusive, the probability that A or B will occur will be something like this: probability of A plus the probability of B, which is what we saw with the blood types. Oh yeah, like the probability of the additive property. I got you, good deal. So basically, in the situation, here is your entire population. You're just trying to find what's the probability of this one or this one. So I get to combine these two probabilities of selecting it. Like for instance, if I take maybe I want the probability of type A or a type B, then I can add the two results up out of the population of all blood types, like that we saw earlier. So let's look at an example to make that make more sense. So this one says, at a convention, there are 7 mathematic instructors, 5 computer science instructors, 3 statistics instructors, and 4 science instructors. None of the instructors teach in more than one discipline. If an instructor is selected, find the probability of selecting a science instructor or a statistic instructor. All right, so how many instructors are there in total? No, in total. 19. That's going to be 7 plus 5, which is 12, plus 3, which is 15, plus 4, which is 19. So there are 19 total instructors. A is the first event. So the A is going to be being a science instructor. B will be being a statistic instructor. And so now we're going to figure out the or part. So what's the probability that you are a science instructor? Okay. 4 out of 19, right? Then what's the probability of, go ahead. No. Well, technically all of these are sciences, but more specific under the science department, because math is technically a science as well. Part B is the statistic instructor. So how many statistic instructors are there? 3. So that becomes 3 out of 19. And then to add that, what's 4 plus 3? So this becomes 7 out of 19. Right? That's it. So when you're looking for mutually exclusive, because you cannot select, again, this goes back to the voting thing, but each event can't happen at the same time. I would select one person and then select another person. I would be okay with just 7/19. Like, to me, I get that you just did 4 plus 3. Like, a lot of this is, there's not like, it's not like college algebra where there's like a lot of work to show. I'm totally good with some simple, like, I get it. Now, if you get it wrong, there's no work, then I got nothing to and go back. So it's never wrong to show as much work as you can. Any other good questions like that? All right, so let's look at the addition rule 2, where events are not necessarily, that's not, see that word itself just makes that a little opinionated. So events that are not necessarily mutually exclusive. So when two events A and B are not mutually exclusive, the probability that A or B will occur will be if you add the two and then you have to subtract it. So meaning if it's not mutually exclusive, then the same event can happen. Meaning the heart and a face card, right? I can draw it once. Can both events happen? Yeah, so it's not mutually exclusive. So I got to find the probability of getting in the heart, which is, if y'all don't know this, 13 out of 52. There's 13 cards in each suit, and there's 52 total cards. And then I have to find the probability of a face card. So that's 3, 6, 9, 12, 12 out of 52. But then I add those up, and that's 25 over 52. And you're like, okay, that's my answer. But you doubled up somewhere. You doubled up hearts and face cards. How many are hearts and face cards? 3, right? So then I would have to then take that result and subtract 3 out of 25 from that. So this is if they're not mutually exclusive, meaning the event can happen twice. I find the probability of each, like we've been doing, but I have to subtract them doubling up, right? So that basically what happens is you counted them twice and you're deducting one of them back out. And that would be your probability of getting a heart or a face card. Go ahead. The what? Right. Okay. So yeah. So P of A or B is either the probability of A happening or the probability of B happening. Because remember, when we see or, we add. But if I count all of my hearts and I count all my face cards, I have some that are both hearts and face cards. So I have to subtract that so it only counts it once. Gotcha. So again, this rule can be used when events are mutually exclusive as long as you recognize that the probability of A and B equals 0 because they cannot occur at the same time. When two events can happen at the same time, P and A is included in both PA and PB. So for example, that one we just did with the instructors, if I'm selecting one person at a time, there's not one person that's both a science and a statistics instructor because they only teach one discipline. So therefore, the probability of both it being a science and a statistics teacher would be what? 0, because that's impossible. It's an impossible event. But in this situation, like with the card situation, the probability of getting a heart and a face card was 3 out of 52, right? So then that now is 3 out of 52, which then what I would subtract from my total. Okay. So if it's mutually exclusive, this is going to equal 0. If it doesn't equal 0, then it's not mutually exclusive. So again, to see a more of a Venn diagram there, here's event A happening. This is all your hearts. This is all your face cards. I got to subtract what overlaps so that I only count it once. Don't know biology. I'll just take your word for it. All right, let's look at example 11. Maybe this will make more sense. All right, so in example 11, it says, suppose there is a study involving 300 patients. Of the 100 alcoholic patients, is this like your homework? Very nice. 87 had elevated cholesterol levels. Of the 200 non-alcoholic patients, 43 had elevated cholesterol levels. And the results are summarized in this table below. All right, so they'll typically do all the math for you. Does everyone have this? I'm going to scroll down so we can get into what we're finding. So here's our solutions. So if I want to find the probability that alcoholic with elevated cholesterol, in this situation, I'm looking for both events to happen. All right. So they have to be an alcoholic and they have to have elevated cholesterol. So when I look at this chart, I'll scroll up real quick so you can kind of see it. Right, but so that's the issue. So a lot of people have they're trying to total all this. So I have to go, all right, how many are alcoholics? There's 100. And then with elevated cholesterol is 87. So that's 87 out of what? Oh, wait, hold on. Yeah, because you're trying to select them out of a total. Okay. Which is then just 300. I see what you're talking about. You're talking about like people with elevated cholesterol, but there's a wording here. We're just trying to find the probability of alcoholic with elevated cholesterol out of our total people. So if I would say that they're first, and that's probably on your homework, so we're probably going to get there here shortly. But if I ask, what's the probability that they are alcoholics and have a high cholesterol? This is simply just saying that they're alcoholics with high cholesterol. So that would just be the 87. So, and we're going to get to that here, but that's probably what you're struggling with on your homework, maybe. Because I know I remember doing that when I was in high school and college. But if it says the word and, so what we have to do is the first event has to happen. So I need to look at all of my alcoholics, which in this case would be 100, and then and have high cholesterol. Now it's going to be 87 over 100. But because I'm just looking for alcoholics with high cholesterol, then I'm going to just look at the total, which is 87 over my total population of 300. So that with there. Well, 87. Yeah, 87 out of 300. So because of this word right here, alcoholics with elevated, so that's going to be straight up 87. And then your total patients is going to be 300. But had that been alcoholics and elevated, then I'm going to just look at just the 100 as my total patients. That does. That right there should be, that should be a with, because that's a different question. Because it's, again, if you have the number of patients are alcoholic with elevated cholesterol, that's just going to be this one. But if it says and, this changes because my surveys, they have to be alcoholics first. Yeah, so that should be a with as well. Right. You have to look at this number. But if you put the word and there, then they have to be alcoholics first. Then we look at elevated. Oh, talk about this total number. I got you. Yeah, but they didn't have to write the word and. They have alcoholic with elevated cholesterol. That would be only this category. They have the word with right here. I got you though. All right. Questions on that one? So keyword and vocabulary there. So then in part B, we're looking at just non-alcoholic. So then when I look at my category, my non-alcoholic, I need to go all the way over to what? 200. So I'm going to have 200 that are non-alcoholic out of how many people I have? 300. So this would just be 2/3. I don't know if the other one can simplify. 87, I think, is prime. And 87 isn't prime. Is it by 3? Yeah, so I could go further on that one. So 87 out of 300. By that by 3, that would be 2, 9, 100. So 0.29. All right. This one here is alcoholic or elevated cholesterol. So the first thing I do is find out all of my alcoholics, which in this case is how many? So this would be 100. And then how many patients did I have? 300. Now I got to find out or, so with elevated cholesterol, so that's going to be a plus for or, with elevated cholesterol. So that is what? No, that you'll get to that. So I want all with elevated cholesterol. How many are 130. Then you'll subtract, because this is because you could technically randomly select. That's 130. 130 over 300. I don't know if that's better or not. All right, so then I need to find out the probability that you select both of them so I don't have the overlap. So the probability that they're alcoholics with high cholesterol is how many? So again, I'm looking for ones that are alcoholic with high cholesterol. So this would be 87 out of 300. So now I got to do is just add and subtract. So 100 plus 130 is minus 87. Very good. Add 300. 143.78. I'm pretty sure that's prime. We're going to go with that. It's not 2 or 3. Maybe 7? No, not 7. 9? 53 now. Oh, it is 9. 9 goes, sorry, my brain went somewhere. No, it's 53. No, it'll be 63. It'll be, okay, go ahead. Sorry. Oh, so you're just adding in the rest. If you did that math already, yeah. Yeah, if you went ahead and took that, yes, that's fine. But a lot of sometimes these charts get a little bit bigger, so sometimes that's not as obvious. But if you see that, by all means, yeah, I'm good with that. Yeah, it would be if it was 153, then it's divisible by 9 because it would be 9. It would be 20. No, it would be 19. All right. So D then we're asking probability that not with an elevated cholesterol or an alcoholic. So I got to find, this is an or. So I got to find ones that are not with an elevated cholesterol. So how many do not have elevated cholesterol? 170 out of 300. Huh? Not straight up because this or. Then plus they're an alcoholic. So how many are alcoholics? 100. But then I got to subtract the ones that are alcoholics with not elevated cholesterol. And how many is that? So 13. So then what's 170 plus 2? What's 170 plus 100? And then subtract 13. So 257 out of 300. All right. We'll finish up 4-2 tomorrow, and then 4-3 and 4-4. We're literally almost done with 4-2. Do make sure you are working on y'all's homeworks.